Thank you. So this talk is about vispy, which is a scientific, or actually a general purpose visualization library based on OpenGL. And some of you might remember last year we kind of introduced the project. And back then it was the case that in order to use the project, you needed to know about OpenGL. And then back then we sort of promised we are going to work on higher level layers to hide OpenGL from you. And we've worked quite hard in the past year to achieve that, and we've come a long way. And so this is sort of a status update of where we are now, what you can do with vispy, and how we go from here. So data is becoming ever more ubiquitous. So you have larger data sets, you have complex kinds of data, and we kind of want to move away from looking at a static image of the data towards interacting with your data. For instance, if you have a three-dimensional image, you want to be able to look at it from different angles in order to really appreciate all the detail. But if you want to do that, you need high performance, because if you have bigger data, then you need more speed. But if you want to make it interactive and run at 60 frames per second, you need even higher speed. So you cannot get away without going to the GPU for that. So that's why we're based on OpenGL. And actually, with modern OpenGL, you can influence to quite large extent what's actually happening on the GPU, what code is executed there. So if you design that code appropriately, you can actually make very high quality graphics. For instance, take anti-aliasing, you can handle that quite good. So you can achieve a quality that's quite similar to, for instance, Matplotlib. So the goals of vispy, well, it's sort of a general purpose visualization library, but we target primarily at this point scientific visualization. But if you want to write a game, it might actually be quite useful as well. We kind of try to make it very easy to install. So until now we've achieved to keep it to pure Python. We hope that we can maintain that. It's also the goal to make it easy to use, but also at the same time make it very flexible. And we kind of apply a modular structure to achieve that. Well, as I said, we really aim at interactivity and fast visualization, but at the same time have a high quality. And we have support for quite a lot of different backends, so you can embed your visualization in a Qt application, WX, GTK not yet, but surely that will come. And we have backends for the IPython notebook, which we'll demonstrate in this talk. So just a little bit of background. vispy started with 4 developers we all had our own visualization toolkits based on OpenGL, and we realized that we're doing much the same things. So we started to collaborate like a year and a half ago, and that's how vispy started out. And like a little bit more than half a year ago, Erik Larsen also joined the team, and he has really done a lot of good work in making sure we have unit tests and adopt good style standards and getting continuous integration. And since then has done a lot of other things as well. And we've had quite a few contributions from other people as well, some of who are in this room. So the structure of vispy, so these are all the modules, or most of the modules in vispy. On the left-hand side are all the modules that are directly related to visualization. And you could consider them kind of stacked on top of each other. So the top one is the Gloo is really the basic, sits directly on top of OpenGL. And on top of that, we have different layers which use the lower levels for their task. And as you go down, you kind of get in higher level layers, so you get better abstractions, but slightly less flexibility, of course. And on the right-hand side are a couple of support libraries, so to speak, that don't directly relate to visualization. And well, the most important one probably is vispy.app, which gives you a very easy interface to create a window in which you can do your rendering and visualization. So in this talk, I will mainly talk about these things on the left-hand side and just start with the top one and go all the way to the bottom. So Gloo is the object-oriented interface to OpenGL. So it provides a very Pythonic API to OpenGL. So it's probably one of the easiest way to use OpenGL. But still, yeah, you need to know about OpenGL. You need to write your own shaders. So it's not very useful for a wide audience. You can make very pretty visualizations with that. It's a bit stretched now due to the rescaling of my monitor, but this is not a scientific visualization yet. So on top of this, we create another layer. Basically, actually, the visuals are actually part of the scene graph layer, but you can use them on themselves. So I cover them in this order. So a visual is basically a Python class where you wrap up all your Gloo stuff. So someone who knows OpenGL and Gloo can then create a visual. So you're now talking about higher level concepts. So you're not talking about OpenGL buffers and textures and things like that. Now you're talking about lines, markers, images, meshes, volumes, volume rendering, etc. And we kind of plan to have like a large variety of these visuals in vispy, so it's sort of batteries included. But at the same time, it's quite easy to extend this functionality, so to create your own visuals. And we try to make that quite easy by giving you tools so that you can sort of take different code snippets, so that's shading code that's executed in the GPU. You take different snippets that are already there and you smash them together to create a new visualization. So this is a visual. So this is an image visual, for instance, and the image visual has a method called setData, and right now what it's doing, it's loading data, or reading data from a video file and using it to update the image, or having a feed from the webcam. So that's the visual. So the scene graph, or the vispy.scene, is then the next layer that's on top of that. Or basically it extends the functionality of visuals. That's maybe a better way to describe it. So some of you might know what a scene graph is. So basically the concept between different scene graphs implementation is quite similar. The basic object, the basic unit in a scene graph is what we call an entity. And an entity is quite a simple object. It has 0 or more children, and it has 0 or more parents. And you can kind of create a hierarchy of different entities, and so you build up a scene graph. That's where the name scene graph comes from. And every entity also has a transform, and this transform determines how the entity is transformed with respect to the parent. For instance, if you have a couple of sort of hierarchy, if you have a parent and you change the transform of that parent, then all the children transform with it simultaneously. Some important subclasses that you should know about is the visual. So we basically just covered that. So the visual is basically an entity that knows how to draw itself. So it has a draw method, and then it does some Gloo, some OpenGL stuff, and then it will appear on the screen. The visuals are sort of designed, so you can use them in a scene graph, but you can also use them without a scene graph. Basically, you create a visual without giving it any parents or children, and then you sort of have a more basic, more raw way of working with it. The view box is basically what most people will know as a subplot. So it's a rectangular area to which a scene is drawn, and that scene is basically the children of that view box. So the children of that view box, it's not entirely true, but for the sake of example, it's the easiest way to say it. These children, they form the sub-scene, which is then rendered to this rectangular area. And the way in which this rendering is done is determined by a camera object, which is associated with the view box. And this camera also defines how user interaction is done. So you can have a two-dimensional camera where you can do dragging and zooming, but you can also have a three-dimensional camera that will float around or whatever. So to put this in a picture, well, very briefly, we have a canvas, so it's a window on your screen, and in there we have two view boxes, one on the top, one on the bottom, and in the top one you have two lines, in the bottom one you have a volume rendering with some arrows. So you get a sort of scene graph as you see here. And in the right-hand side, you can see that the camera is actually an entity. So the camera lives in the same scene alongside the volume and the arrow. And this means that you can just position the camera and orient the camera, and in that way influence how the how the scene is rendered. And that's quite convenient. I'm going to skip over this. So this presentation is actually made in vispy. So all these slides, every slide is one view box, and all the text that you see are text visuals, basically, which are in the scene of a view box. And in there, the blue area over here is sort of a view box inside this scene, and I can manipulate the data. And I can also sort of go in there, sort of make this sub-view box my top-level view box temporarily. So that becomes sort of full screen. And I can also do the other way around. I have like, I don't know, 20 slides or so, and they live in a scene somewhere behind me, so to speak. And I can actually show that and attach a 3D camera to it. So these are all my slides. It doesn't, you see that it doesn't, the clipping isn't quite right. But every one of these blue rectangles is one view box and one slide in the presentation. So this is an example of kind of simulating view boxes. So these are 400 lines which are constantly being updated. And well, right now, in the current state, if you would create 400 actual view boxes and have a line in each one of them, that will be incredibly slow. But there are ways, we're pretty sure that we can optimize this by sort of grouping together or visuals of the same type and putting them in a collection so that you can draw that using one OpenGL call. And this is sort of a proof of concept based on Gloo to demonstrate that something like that is possible. And you can actually do clipping of the view boxes in a fragment shader. And it's very, it runs at 60 hertz just fine. So once we implement that, you can actually create actual scene graph view boxes and make something like this in a normal visualization. So I work for a company called Cinoptics, and they build head-mounted displays for virtual and augmented reality. And one of the benefits that vispy brings for us is that it's the way in which the scene graph is designed makes some things quite easily. For instance, because every entity can have multiple parents, we can actually, we kind of have one view box for the left eye and one for the right eye, where we don't have to duplicate this scene that we're visualizing, because it's the actual same scene, but it's present in both, in both view boxes at the same time. And another very nice advantage is this way that the camera operates. So you can, if you have augmented reality applications, what you do is you use a tracking mechanism so that you know where the head of the user is and what its orientation is. And we can just push these values into the camera and it will just work, and we don't have to fiddle with transforms. Sure. So on top of this scene graph, so I think the scene graph is sort of the top level where we actually add functionality, and right sort of on top of that we add more like user friendliness in terms of a functional interface. And one that we already have is vispy.MPL plot. So this is an example that actually works. So you can do from vispy import MPL plot as PLT, do all kind of matplotlib stuff that you want. And at the moment that plt.show is called, we kind of grab the figure and we serialize it into JSON using code that's written by Jake Vanderplas. And then we sort of unpack it into a vispy figure, and then you have all your high-performance interactivity. And you can actually play with this already. It's not really complete, but it's at least the API won't change, so it's quite safe to play with it. So. I want to show a demo in the IPython notebook because we have a IPython notebook backend. Actually, we have two. So you can import a couple of names from the vispy namespace. If you do IPYNB static, basically what it will do, it will render one frame and then make a PNG and send that to the browser, and that's it. So we have a static image, which is not very exotic. So the other approach that we've implemented, so by the way, this was done by the Google of Code students. Right now, you can, instead of having one image which is being sent, you constantly keep updating this figure, and at the same time, in the browser, you are collecting user interactions, and you can send these back to the process where they're just entering the normal vispy workflow basically, and you have a fully interactive visualization. So this is a Gloo example, so we're actually using OpenGL directly in the IPython notebook. So this is basically the center way of doing an IPython backend. Another approach that we haven't done yet, but we plan on working on, is instead of sending images, sending OpenGL commands, which are then executed in WebGL, and then you can really have high performance fluid visualizations. So to wrap things up, so some of the lower levels of vispy are quite stable in terms of API and their workings. Vispy.scene, so the scene graph stuff, is really going to be a way for everyone to benefit from these kind of visualizations, but it's kind of alpha status. There are some things that we need to do, like picking, transparency, collections. But if you have an interest in this, I encourage you to try it out and give some feedback, because we are also very interested to know in your needs so that we can take these needs into account in the design process. But just be aware that the API is quite likely to change. If you want to play with vispy and just do it very safely and easily, this vispy.mplplot plot is a very easy way to get started. We don't have everything working. We don't have text at the tick marks, for instance, but at least this API is stable. And further, we have a sprint tomorrow, so if you want to come by and help out, then you're welcome. And that's it. Thank you.
So we have time for a short question while the next speaker please lines up and set up the laptop.
So I'm trying to figure out how I get this working from Julia. When you do it in the notebook and you drag on it, it also. Are you using the IPython widget protocol for that?
Yeah.
Oh, you are.
So right now we're using the IPython widget protocol, which is quite a convenient way to get this working. It wasn't that hard in this case, but it's not very efficient because the widgets are sort of designed to communicate or to keep the state between the client and the server consistent. And it's not really made for high throughput communication.
So you drag basically, it sends a message, you re-render to an off-screen buffer, and then send the ping image back.
Yeah, and especially sending these images is probably not the most efficient way. So doing that using a binary socket, which I think there's a PR for, would be much more effective. But then we'll have to, make some kind of area to draw to. So there's some bit more complexity then, but it would be possible to make it more effective. But the WebGL solution would even be, would be the ultimate solution in this sense. Yeah.
Thanks.
Another short question? No. Yes.
So in terms of 3D features, can you compare that, what you have currently with, I don't know, VTK in terms of abstractions? Is that something?
In terms of 3D features?
Yeah, for example, the kind of geometries that you can represent.
Well, basically you can create any visual that you want. You just have to make the visual, and then you can use that. For instance, we are working already on some volume rendering. So a volume visual which implements volume rendering. But you can also, certain VTK visualizations, you can sort of implement them in a visual, and then other people can use them quite easily. Does that answer your question?
Okay, so thank you, Almar, again.